thank the organizing committee for having me today. I'm really happy to be here to talk to you about revelations in monitoring and why environmental monitoring is not just for leakage anymore. And by the end of this talk, I hope to convince you that, in fact, environmental monitoring should not be for finding leakage in a geological CO2 storage site, but it should be more for responding to stakeholders' concerns. And the reason why this is so important is because the IEA has said that we need to upscale CCS by 2 orders of magnitude to where it is right now by 2050. And even now, with CCS minimally deployed, we have learned some very important lessons. And I think it's extremely important that we heed these lessons now so that the transition to upscaling can be done in a way that is smooth. And I need the clicker. Thanks. Okay. Yes. Okay, so interesting. You know, it's difficult for a lot of stakeholders to kind of wrap their mind around how you put CO2 deep in a rock. But what I found is that it's the environment that people care about. It's where they live, it's what they see, it's where they can understand CO2 storage. And so really environmental monitoring is the interface between the project and the public. And so being in environmental monitoring, I get this question all the time. Is it safe? Will it leak? What happens when it leaks? And the answer to that question, and I'm sure many of you have been asked this, and I think a very good answer to this question is, you know, geologic storage is safe by design. I mean, as geologists, we know the right places to store CO2. We do site characterization. We have to get the site permitted. There has to be a high level of assurance for this. And then we do risk assessment using modeling to identify any potential unwanted outcomes. And then to further minimize any potential risk, we design the project. And then we monitor it. And we monitor it both in the deep subsurface. Let me see if I can make this work. Oops. Where is the pointer? There it is. So we monitor in the deep zone, in the reservoir, and in the layers above. And then we monitor in the shallow subsurface for assurance. And this is to ensure that no unwanted outcomes are happening to the environment. And those areas are the shallow groundwater, the vadozone, and the biosphere. Now, my expertise is in the terrestrial area, but all of these concepts can also be relevant for the marine environment. So what I'm going to be talking about today is the vadozone. So this is basically the sediments that are just below the surface and are the interface of the subsurface into the atmosphere. So that's what we're going to be talking about today. And these happen to be the very resources that we want to protect. So we have put a lot of great science into finding leakage. And we have all kinds of ways that we can go about trying to find leakage. But what I would say to you is that when we do that, what are we actually doing? Are we really finding leakage? Well, actually what we're doing is we're finding areas that have a lot of CO2 and areas that don't have so much CO2. So here we have the Weyburn-Midale site. This is CO2 concentrations in the shallow soils. And here we see areas of high CO2 and areas of low CO2. And this is naturally occurring CO2. And then if we look at Laterra, which is a volcanic area, and a lot of times geochemical monitors like to use volcanic areas because they kind of are an analog. They can be seen as an analog to leakage because the CO2 is coming from deep and is coming to the surface. Here the CO2 is being created in situ in the shallow subsurface by biological respiration, but here we see CO2 coming from deep and coming up to the surface. It doesn't look really any different. We just see blobs of CO2 here and no CO2 there. So what we have to realize is that CO2 is extremely variable in space and time, and it is naturally occurring everywhere in the sediments. The dominant source, as I said, is biological respiration, and it's very dynamic and it's also reactive. It dissolves and it reacts with soil carbonate. So it's really difficult to discern any kind of a leakage signal from natural variability, and it's difficult to determine what is actually anomalous. So how have we been doing this? Well, we've been determining anomalies using baselines. And what this is that you measure the baseline CO2 for 1 full year before a project begins to document the seasonal variability in the carbon dioxide. And then, over the lifetime of the project, you monitor CO2. And if you see any kind of a significant increase of CO2 during the project, then that signals a leak. But there's a problem with this. And the problem is that you're not finding a leak, you're finding anomalous CO2, something that looks anomalous. Then you have to further go and ask the question, did the storage project cause the anomaly, or was it just a natural fluctuation that caused the anomaly? So attribution or source attribution of that anomaly is a missing step. And in fact, I collaborated with Tim Dixon on a 2015 paper where we looked at 8 global regulations in CO2, global regulations in CCS, and what we found was that out of the 8 global regulations, 7 of these regulations say that we must go out and detect leaks or anomalies. And then 5 of those 8 global regulations say we need to use baseline and background measurements as the way to determine leakage versus natural variability. But when you look at attribution, it is missing. It is a missing step. It's not something that is brought into the consciousness of the people that are doing the monitoring. And yet it is an extremely important step. And in fact, if you look at it, the regulations actually say that you find the anomaly using baseline methods, and then you start quantifying. But we don't want to quantify something unless it's a leak. So it's really important to use attribution. But there is another problem that we have recently come upon understanding, and that is that baselines in soils are shifting upwards because of global climate change. This is a paper from Nature, and here you see the flux of CO2 from the soil into the atmosphere from 1960 to the 2000s. And we see an increase due to the increase in temperature. We see an increase in the respiration. Baselines in groundwater are shifting upwards. And as we all know, baselines in seawater are shifting upwards. And so what is going to happen if we measure CO2 at the beginning of a project and we use baselines as attribution? Well, here is an example from one of the projects that I have been monitoring at the Cranfield site in Mississippi. This is the background CO2 concentration over 6 years. Look at that incredible shift upward over the time that we monitored. And we thought, okay, is this leakage? Well, we just happened to be able to use carbon isotopes in this case because the injected CO2 that was being put in was delta C13 of -5, but the soil gas CO2 basically stays constant. So we know that's not leakage. That is natural CO2 respiration rates rising. So what I want to ask you is, if we had used baselines for attribution, in the first year, by the second year, we would have had a leakage signal, but it wouldn't have really been leakage. So this is really important. This is an important lesson. This is revelation number 1. Naturally produced CO2 in the biosphere is increasing due to climate change, and if we use baseline for attribution, it's going to result in false positives time and time again. And again, like I said, storage is safe by design. So the risk of false positives using this method is actually greater than the risk of leakage itself. And false positives are going to put projects at unnecessary risk. How do we know this? Well, I'm going to talk about the Tomakomal Project. The Tomakomal Project is an offshore demonstration project in Hokkaido, Japan. They did everything right. They did everything that the regulations say to do. They derived their leakage thresholds based on a year of baseline, and they used routine monitoring of the seawater column. But it only took 1 month of routine monitoring to find a CO2 level in the seawater column that was above the threshold. So 1 month of injection, 7,000 tons, the project was suspended for almost a year while they worked out whether that was leakage or not. So you see, this is really happening, and we need to really be careful that this does not happen. Because this is a project that, like I said, everything was done correctly. Shifting baselines called false positives and project shutdowns. So revelation number 2 is that if we actively look for leakage, we're going to find it. We're going to find an abundance of anomalies, and then we're going to have to attribute them. And baseline methods just are not effective at this. So how are we adequately going to assure environmental safety? Well, I think we can take a clue from another experience that we had, which was the 2011 Kerr leakage allegation. So what happened here was that this happened at the IEA GHG CO2 Monitoring and Storage Project in Saskatchewan, Canada. And what happened was farmers living near the project saw changes in their land, such as bubbling in their ponds and strange growths in the pond and on the surface of the water. And they looked at that and they said, wow, our farm is changing. We think it's leakage from the storage project. And so they tried to get help, but there were no protocols for responding to their concerns. And so over and over and over again, they were not satisfied at the way the operator, the government, and were responding. And so they took matters into their own hand, and they actually hired their own consultant who was inexperienced, and of course attributed wrongly that leakage was indeed occurring. Well, what came from that? A very negative media storm, some amazing headlines here. CO2 levels could asphyxiate you in one place. Foot goes the promise of pumping CO2 underground. This was extremely damaging, and we were actually called out as one of the teams to go and attribute this. And it took time to mobilize a team to go out there, to look at it, to do the science, and to say, okay, indeed, this is not leaking. But even to this day, oh dear, I need to go backwards. Even to this day, some people still believe it is leaking. Once the damage is done, it's very hard to take it back. So we need to make sure that this doesn't happen to begin with. So revelation number 3, environmental change is going to result from climate change, and stakeholders living near these projects are going to see things happening in the land, and they're going to see, is this, coming from the project? So when CCS is fully deployed, responding to stakeholders' concerns may be our main activity, and we really need to develop fast, accurate, stakeholder-friendly methods to communicate that leakage either is or isn't happening. So at the University of Texas at Austin, we are very aware of this because of our experience. And so we have been developing a method called process-based ratios. And instead of looking at concentration, we're looking at the processes that cause the gases to be what they are. So we're using the stoichiometry of the important vadosone processes to try to understand. And the beauty of this method is that, first of all, it's not baseline. It does not rely on baseline, so you don't need to take years of data. And you only need a one-time characterization. And the method can be applied anywhere. So I'm going to just briefly run you through one of these relationships so you can kind of understand what this is all about. So if you start with atmosphere, which is about 21% oxygen and about not very much CO2, biological respiration, for every 1 mole of oxygen that is used, you will produce 1 mole of CO2, and it will draw you down that respiration line. Now, take a look at that respiration line. That's important. I'm going to talk about that again. But we can do even more than that. We can do more processes. So, for example, if we have a methane-rich environment, we can look at the oxidation of methane to CO2, because for every 2 moles of oxygen, we create 1 mole of CO2, and you bring it down that line. Anything that has less CO2 than its corresponding oxygen is CO2 dissolution into recharging water. But anything that has too much CO2 for its corresponding oxygen could signal a leak. So this is a very simple screening process that we can use to immediately go in. And the beauty of it is that it is also very user-friendly. It's very simple. We could even stick a sensor in someone's backyard and say, look, here's the graph. If you see anything, if you see a data point every day, a data point can come up on this graph, and we can tell the stakeholder, anything on this line or to the left of this line, everything's good. If you ever see anything go to the right of that line, then call us and we'll come check it out. So it's very simple, and it's instant, and it's easy to explain and engage stakeholders. So, for example, if we go back to my first example, which was these variable CO2 patches and blobs, at Weyburn, it was natural CO2. And in fact, these are the data from the Kerr site that we did, the attribution at the Kerr site. Everything was either on the line or to the left of the line. It was natural. It was not leakage. If you would go to a place like Laterra, or a place where is actually finding a leak, CO2 is actually coming to the surface, then you're going to get this concentration to the right of the line. And these data are actually from a controlled release experiment at the Zert site that we use to show that indeed and in fact leakage will manifest to the right of that line. So the way I'd like to end is by just saying, sometimes the reason you have to learn lessons the hard way is because you didn't learn them the first time. And I know it's really hard for monitoring experts that have been, we've just been like baseline, 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 baseline. But I really think that we need to start stepping away. We need to ditch baselines, actually. We need to step away from baselines because they are not going to do anybody any good at all in geological CO2 storage monitoring. So let's learn from our experience now. So in summary, again, CO2 storage is safe because we design it that way. But baselines should not be used for attribution because they are shifting. And in fact, I would say to you, I don't believe they even exist. I don't believe baseline even exists as a concept anymore when we're talking about environmental monitoring. We desperately need to update the protocols and regulations because this is what they're outlining for the protocol. And then we learned from the Tomakomal Project, we learned from the Kerr claim. And so what we need to do is we need these accurate methods and protocols for attribution. And when you think about the fact that the risk of a false leakage claim is higher than the risk of actual leakage, then we need to make sure that we avoid these false leakage claims. And like we said, I think if we could all go out and start developing some methods that rely on characterization rather than a time series of measurements, then I think that that's going to be useful for us. So that is it, and thank you so much for your attention.
Thank you, Katherine, for giving a very good overview of storage and leakages and so on, because that's one of the things that is all people are worrying about when they are living next to storage. So, are there any questions to Katherine?
There's one.
There is one up there.
Yeah, I know.
Hi, I'm Daniel Soto from Climeworks. You showed the C13 method to detect whether the CO2 is fossil CO2 or natural. That seems to be a pretty simple and safe method to determine the origin of a carbon atom. Excuse me. Do you see that as a significant threat towards developing BECCS and storing biological CO2?
Okay, that's a great question. Thank you for bringing that up. So that illustrates the point that for us, a process-based method is a very quick and easy screening method that will probably screen out, 90% of the anomalies that we find. But the remaining percent that maybe show something to the right of the line, they need more assessment. And carbon-13 is not going to be useful all times. That was an interesting project because it was using CO2 mined from a natural dome. It was not anthropogenic CO2. When we use anthropogenic CO2, carbon-13 will not work. Carbon-13 would work better with potentially with biomass, but it just depends, like you said, on what the CO2 source is. But what we're finding is that if we use delta C13 versus carbon-14, then we get a really powerful way of attributing the remaining anomalies. But carbon-14 is extremely expensive, and you would not use that as a screening tool. So yes, the next smaller percentage of anomalies, we're going to need additional attribution. And in fact, I've just been working at the CTSCO site in Glenhaven in Queensland, Australia, where the Analec R&D program has funded us to do a complete characterization of all the potential signals that we could see in the near surface to try to understand exactly what the delta C13 versus carbon-14 would do for attribution in that area. So thank you for that question.
Great. We don't have time for more questions, unfortunately.